operating system project that we're working on in the computer science department. This is work with Steve Dawson-Haggerty, Jay Tanasia, and a number of our talented undergrads, Sagar, Gabe, Nikita, and of course, David Culler. So we all know buildings are a big energy consumer, and commercial buildings are a big piece of that in the United States especially. But there are also huge sensor networks within these buildings. So the building we're in right now has over 150 temperature sensors in it. It has electrical submetering. It has a lot of fans that you can control the speed of. It has hundreds of dampers controlling how much air is being supplied to different rooms in the building. It has controllable lighting, variable speed pumps, etc. And all of this can be programmatically accessed. There's this wealth of data, of sensing data, and of control capability within buildings that's not often known about. And in fact, there's over 6,000 different sense and control points in this one building alone. Now, you might think this is just a new building, and what about all the other buildings out there? Well, it turns out this is reasonably common. Even old buildings like the Bancroft Library here on campus, built in 1949, has over 5,000 sense and control points, and largely because those get installed as part of HVAC retrofits that are relatively common. And so what we observed is that these buildings are not being run to their full. No one's taking advantage of all this capability nearly as much as it could be. So there's a ton of different exciting applications that we could imagine enabling within buildings. Everything from, of course, you might think about saving energy. I'll talk a little bit about this ventilation optimization app that we implemented in this particular building. You might imagine new forms of occupant control. Are there things that individual users might want to do with their building? You might think about fault detection. This is another paper not from our group that's looking at ways to automatically detect problems within the building so that the facility manager's job becomes a lot easier. There are groups that are doing MPC for other forms of energy optimization. So there's a lot of potential that you might enable within these buildings. Why isn't it being done? Why isn't this happening at scale? There's a number of challenges there. But the goal we ultimately want is to be able to essentially instantly deploy these novel applications across all compatible buildings. Why is it that when someone in this group has come up with a great idea for how to run the building, we can't just, at the click of a button, deploy that across all compatible buildings in the same way that you might with a web page online or Gmail or anything like that. And so, of course, there's a number of challenges, and these are just the ones that we begin to address in the Building Operating System project. So first, there's portability. Of course, all buildings are custom designed, and so they're different, and I'll talk quite a bit about that one. There's fault tolerance. What about things breaking? Is this going to cause problems within my building? How can I ensure it's still reliable? Multiple processes. Can I actually allow 2 or 3 or 4 of these different applications to coexist within the building? Today, that's not the case. The building's programmed once, and that's the way it works. Federation. Can we put together systems from multiple different vendors and make this work? And then, of course, scale, security, and privacy. So we don't claim to solve all of these, but these are the type of problems we're tackling. So this is the architecture that we've designed. This is all, there's more detail on all of this in a paper that's called BOSS and published in NSDI this past year. But essentially, we've built up a layered software architecture. At the bottom, there's a hardware presentation layer, which talks to multiple different control systems. Then there's a hardware abstraction layer, which deals with differences from building to building, and I'll talk quite a bit about that. There's a number of services above that, transactions for safety, time series data, etc. And then finally applications that run on top. So I'll cover a couple of these pieces today. So first, digging into the challenge of portability. As I mentioned, of course, custom buildings are unique in some sense in that they're custom designed. So this is Satarja Dai. And this custom design goes down to things like mechanical systems. The ductwork and the placement and interconnection of the different components is going to vary from building to building. It's going to vary from control system to control system, too. This happens to be the Siemens control system for this particular building. You'll notice it has some of the individual HVAC components in there, how they're put together, shown graphically, but then also things like these point names, which are where the sensors and actuators actually are. I'll dig into that in a little more detail. And then, of course, buildings have their own control logic, which I don't expect you to read, but in this building, this is some of the code written in this basic-like syntax that controls how the building is actually running. And so, because of all of these heterogeneity, it becomes really difficult to control buildings programmatically. So, for example, if I want to do something simple like change the temperature at my desk, and suppose I want to do that with a program as opposed to by calling Domenico, who would know exactly how to do that very easily. But suppose I want to do that, and I'm sitting over here in this area on the floor upstairs. What I'd have to know is, okay, so my desk, it corresponds to these couple of ducts that are overhead, and those are controlled by a variable air volume system that has a particular name, S421, for example. And maybe you want to know that that's supplied by a particular air handler for your building. And then you'd have to know that VAV internally has cold air that's being supplied, and there's a damper that controls how much of that air is supplied to your space, and a heating element that allows you to heat that air up. And then finally, I'd have to know that in this building with the Siemens control system, I can command those things by writing to a point called damper command or valve command. And you'll notice these names are confusing. They actually encode a whole bunch of things into the actual name. It tells you the building, Satarjadai Hall. It's modular equipment controller number 8, which is something to do with the network and how the actual controllers are interconnected. It tells you it's on the 4th floor and it's the 21st zone, and then finally it tells you it's the damper. So just an example of what the status quo looks like in terms of controlling buildings. And I should mention that this is just a convention, so this might vary from Siemens building to Siemens building, and then it varies from Siemens to Honeywell to Johnson to whichever other vendors you're working with. So, in a sense, from the computer science point of view, we're working in sort of assembly language. Today, if you're trying to write code for the building, you have to understand both how the building's designed, its architecture, if you will. You need to know how the HVAC system is interconnected and how that relates to spaces. And then you need to know about the control system and how to actually activate and read from that. And you'd have to do this for each and every building. So it's no surprise that we don't get this mass scale that we would want with these interesting applications that people are developing. So the goal, of course, is to get to a point where you write your interesting application once and you can deploy that across all possible buildings where it would apply. So how do we get there? I'll dig in a little bit into this hardware abstraction layer now. And so there are basically two key ideas in here. One is that we need to move away from talking about these kind of arcane names and this hard-coded control based on S421 and start talking about things at a higher level. What about controlling something for a particular room or a particular floor, or maybe I should say change the temperature for all window-facing offices on the top floor of the building. Something like that. That kind of logic can be applied from building to building and still retain its meaning. And the other thing we need to do is move from these low-level languages, low-level protocols like BACnet, which are used to control the building, but are not portable by any means. This is just an example of setting a temperature with BACnet. You'd need to actually be able to fill in all of these values and understand what all that means. And we should go to a higher level semantic language where we use drivers to be able to say, okay, set the temperature for this particular room, make it 70 degrees, and have that be translated into whatever that means for this particular control system. That should be done once, not done by every single person trying to talk to a particular building or a particular vendor. So I'll talk about a little bit of our start on this. We've developed a query language that's based on this navigational database. So the idea is you describe the functional relationships in your building in a graph, which I'll show you in a minute, and then you specify a traversal through that with this basic language, and that helps you write code in a portable way. So this is a sample of what a building model graph might look like. You'll notice there's a number of domains. So we can look at an electrical domain where you have an electrical tree. So the building gets its electricity from campus. There's a couple of submeters, and then that feeds into maybe supplying plug loads for a floor, or maybe supplying certain lights that you have control over. There's an HVAC domain where you take outside air, you blow it through a fan, you cool it down, you supply that to individual rooms where you have dampers controlling how much air is fed into each space. And then finally it enters into the spatial side, where you're looking at what's the layout of my offices, where are my different lighting zones, where are my different HVAC zones. And so capturing all of that, we believe, is essential in order to provide a platform for writing general portable applications. And you can imagine how in my previous example now of changing the temperature at my desk becomes quite easy here. All I need to do is be able to either click or detect where I am on this spatial map. From there, I can figure out which zone I'm in, trace upward, and say, okay, I can control this damper right here. That would control how much air supplies my particular space. Or maybe I even want to know which air handler that is, and I can go all the way up here. And so you can see some example queries here. I can say, give me the lights that supply room 123. Something more complicated, I can say, find all areas that are supplied by the same air handler that feeds into room 123. This could be used for diagnostics. If some room is not getting particular temperature, does it affect other rooms, for example? And it allows a wide range of queries along those lines. I should say that the actual syntax is something we're still working on, so that's not perfect, but that's the general idea of the model. In addition to that, there's a number of drivers which take that low-level backnet and start to give you general methods. And the key idea here is that drivers are built up hierarchically and using interfaces, so standard good computer science design. So for example, all fans might have a get speed and a set speed kind of method, and that could be implemented whether you have a tri-speed fan or a variable speed fan, and it basically controls to what its capabilities are. So that way, if you have a program that needs to control the fan, it'll be able to run across different buildings. So finally, I want to show you what this looks like in practice. I'll talk a little bit about this ventilation optimization app that we implemented in this building right here. So this is based on the fact that in ASHRAE, in Title 24, the code talks about minimum ventilation required for spaces in terms of the amount of outside air per occupant in the space, and then also per square footage. And so the key parameters, the key words in there are outside air and per occupant. So if you can know how much outside air your building is taking in, and or you know how many occupants are in the space, you can control this amount of ventilation that's required. Now, typically, buildings are pretty conservative in this, and as Ed mentioned in part, they often set very high minimums. Partially that's for fear of discomfort, but partially it's also because they make very conservative assumptions about how much fresh air is being brought in the building. The amount of fresh air is actually a constantly changing variable because there's a damper that's going to take in more or less air depending on what temperature the air is outside. It optimizes for reducing amount of conditioning. So we implemented a simple cross-system optimization. We vary how much ventilation we provide to the rooms based on how much fresh air the building's actually taking in. And we observed that in this particular building, being in our nice temperate climate, we mostly take in fresh air on most days. You can see we're almost always at 100% fresh air into the building, which is good from a health and safety perspective. That means we can supply less of it to individual rooms and still meet code. So we implemented this first in BACnet in the traditional, this is what this would look like if you were writing it today. And I don't expect you to read any of this. But then we implement it again in our BOSS stack, and you can see that this becomes much simpler, and you can even understand what it means. You're actually looking at all, you're going to find first all of the outside air dampers for this building, anywhere where you're controlling how much fresh air you're bringing in. And then for each of those, you're going to look downstream of that and find any rooms that are fed by that air handler that might be affected by the fraction of fresh air you're bringing in, and set the airflow minimums there accordingly. That's essentially the logic here. Now, I should say that within this building, we ran this experiment over a couple of weeks, and we saw around 15% of HVAC energy savings from reducing these minimums for all of these different zones. So that's one example of what you can build on this. So in summary, the key idea for this portability component is to express applications in terms of relationships between different system components and to avoid hard coding, as well as to create this hierarchy of drivers that makes it much easier to actually control buildings. So finally, I should say that pieces of BOSS are running in a number of buildings and are in use by folks up at LBNL, are in use by at Aaron's group. The SMAP project that you heard mentioned earlier is a piece of BOSS that we're building on top of. And finally, the takeaways are that there's a huge potential in applying computer science and computer systems design to buildings, that there's a lot we can enable. There's a ton of sensing and actuation capability and a lot of really interesting data that can be unlocked. This can lead to big energy savings. Some of our past projects on lighting showed 60% savings from controlling the lights. And then there's a lot of interesting future systems work here. You can imagine thinking about what do we now do with 6,000 sensor readings at a very high resolution from a number of buildings. If you can get that, is it useful? What if I can do that for a city or for the entire country? And then there are a lot of challenges, like how do I actually verify that my applications are safe and that they'll run consistently across a lot of different buildings. I'll leave it there and take questions. Thank you.
So I just had one question about building control systems as data acquisition systems, that in fact they often don't work very well as such. Do you have any particular way of dealing with metadata issues, like you've got these 6,000 points? Well, so some of them are temperatures. Well, maybe they're sensed once a minute, once every 5 seconds, once an hour. The very rich difference between the data that you see show up, and at the BOSS level, are you concerned about how do you have any understanding of the semantics behind those measurements and how they're applied? Mm-hmm.
Yeah, so it sounds like you're getting at two key questions there. One is, how do you get the metadata? How do you actually get all these graphs that I'm showing you? And how do I actually label all those different points? And you're absolutely right. That's a major challenge in the space. There's a couple of efforts in our group that address this. So you can think about, very basically, it's often captured in things like graphics, like I showed you in the BMS graphics, where you actually see the fan and the different sensors. And so we're looking at ways to automatically extract it from drawings like that so that you can label points more intelligently. You can also, it's often captured in things like architectural drawings where you know where the sensors are within the actual building design. And so we're looking at that too. And then finally, there's a really interesting empirical methods you can use where you can actually actuate components in the building and see how that's reflected in different sensor streams and correlate them and start to say, okay, well, this looks like a temperature sensor, and moreover, it looks like a temperature sensor that is being affected by this VAV, or that's being affected by this air handler. And so looking at things like that starts to address the automatic metadata collection piece. The other part it sounded like you're getting at a little bit is, how do you deal with the volume of data, and are there issues in terms of, can these systems handle it? Can we actually collect as much data as we're talking about here? And that issue, it can be a challenge in some buildings with older networks, but we've put a lot of engineering effort into being able to throttle how much data we're actually pulling from the building, and in doing so intelligently. So for example, if you need to read a whole bunch of sensors and they happen to be behind the same control panel, one simple intelligent thing to do is to read all of those at once, because that's one network request to that control panel, and it can reply in bulk, as opposed to having to ping it individually for a whole bunch of different readings. So those are the kind of things we do. Any other questions?
Hi, Andrew. Carl Brown with CIE. So, deep history, BACNet's original purpose was to enable interoperability of building systems. So, obviously it does that at some level, but not at the level that we're finding to be useful. Where did it go? Where did it go wrong?
Sure. No, thank you. Yeah. So there's a number of challenges. So BACnet does a good job of addressing the low level of how do I actually read or write a unit of data from a number of different points in a building. The thing it doesn't really do is it doesn't do a good job of telling you what that point is or what that point means or what values you can read or write to it. So as I was showing you with these point names earlier on, part of the reason you don't get a rich model in BACnet, you just get a point name like this, is because the BACnet protocol itself requires all objects to have a name. And a name is just a string, and so whatever you use to describe the point, you must capture in a string. Now, there are other attributes you can put in type, and there's even, I believe, an option to put in location. But in essence, it doesn't allow the richness of metadata that you need to describe the actual points within the building. The other main problem is that for things like actuation, it doesn't actually have standards for controlling typical building components. So there's no idea of a standard VAV or a standard air handler or a standard even electrical meter. All of that is left to the implementer. So they can choose exactly both how to name those points and how they work. How do I control damper command? Do I write 100 to it? Does that mean 100% open? Or do I write 1 or 0.1? All of that is left unspecified, left to the implementers. So those are some of the big challenges. All right, thank you very much.
Okay, well, thank you very much for attending the symposium. We look forward to seeing you next year, if not before. And this concludes the end of the symposium this year.